We're good?
Yep.
All right, so a little mini lecture crash course here in circuits, and we're going to start with some symbols. And one of these you're already familiar with, and that's the symbol for a resistor. My version's not very pretty, but anytime I draw a squiggly line on the board, it's a resistor. And I'll get a better marker here in just a second. And we talked about it, okay, but that resistor, if you look at an old school light bulb, okay, an old incandescent light bulb, it looks like the filament in one of those. If you've never seen one, I've got a light bulb we'll pass around probably on Monday. You can look in there and see that it looks like that, and it does provide resistance. That's how those old school light bulbs glow, okay, are part of how they glow, is that there's some resistance in there and the temperature goes up. Another symbol we need is for battery, and we saw that one briefly yesterday, but batteries will have a plus and a minus end, okay. The plus is for the positive, the minus is obviously for the negative terminal, but you need to know that the short end is negative and the long end is positive. That's convention, okay? So this is a battery, and we got sometimes referred to as the positive and the negative terminal. It's like the positive charge and the negative charge in terms of thinking about which way the electrons are going to go, that kind of thing. So we got a battery. Capacitor, similar to a battery, except they are the same length. We've seen that before as well. That is our symbol for a capacitor. And that's all we really need right now. Okay, there will be a few little additions here or there, but that's the big stuff we need right now. When we have circuits, there's going to be drawn circuits or circuits they describe. There's going to be a series of steps that you're going to follow to solve these problems. And once you've done a couple, the steps will pretty much stay the same. So you're going to get, it's like when we did any other type of problem. There'll be, not for this, but it's like for when we're doing force stuff, picture, free body diagram, sum forces, write other relevant equations. There'll be something like that where you'll get into this process that is pretty much the same every time. Okay? And let's talk about some stuff that'll be involved in that process, and that is series and parallel. And I don't think you've read about series and parallel yet. That's coming this weekend. It's part of the reading for this weekend. But series is what you would expect. Okay, if you have a series of things, one thing happens after the other, okay, or they go in order. Does that make sense? If you have like a television series, episode 2 comes after episode 1, that kind of thing, okay? Parallel, picture parallel lines. They won't always look parallel when we draw our circuits, but that helps you with the visual initially. So I'm going to give you an example of two resistors that are hooked up in series. So I'm going to have a battery here. And there's two resistors. Sometimes you'll see it presented for the first time like this, where here's like an R1, and R2, one resistor after the other, okay? How do you really know if they're in series? Well, they might look like this, okay, where one comes after the other, and then it's easy. But what you really have to think about is current, okay, that analogy, that stuff flowing through the wire, okay? The flow of positive charge is defined to be the current. We got. Always put your plus minus on your battery and soon on your resistors. And if we talk about the current, okay, the current's going to flow out of the positive terminal, because remember, it's the flow of positive charge. And in reality, the electrons go the other way, but it's the flow of positive charge. So current will come out here, okay? Picture river, okay, flowing down, okay, or water flowing through a pipe. Has it branched off at all yet? No. So all of the river, or all of the water in the pipe flows into R1. Then it comes out of R1. Does all of the river or the water flow into R2? Is there anywhere else it can go? No, there's no branches here. By branches, I mean there's no forks in the river. Are there any other pipes up here between R1 and R2? No, they're directly connected. So all the water that flows into R1 also flows into R2 in the analogy. That's how you know if they're in series. Okay, if that statement is true, if all the current that goes into R1 is also going through R2, they are in series. And there's something you can do here with the resistance when you have two things hooked up in series. You get to add them. Okay? This acts as like one giant resistor. And hopefully that makes a little bit of sense even without reading, okay? Because they're both lined up, okay? They add up, okay? They will act as a giant resistor. Okay? It's almost like you've have one really big wire here all of a sudden, okay? Squish those two together and you can get an equivalent resistance, okay? An equivalent resistance. So add up, it's pretty easy here. So I'm going to write R equivalent, okay? Meaning what's the total resistance of these two? And it would just be R1 plus R2. Units of resistance. Does anybody pick up on the units of resistance from the reading? Yep. Ohms, okay? And it's an omega. So I'm going to make up some numbers here. I'm going to call this 3 ohms and 2 ohms. 3 ohms and 2 ohms. Okay. little omega thing, ohms? We had a light bulb went off there. No? Someone said, oh. We good? Or a question? We're good? Yep. Ah, okay. There you go. So 3 ohms and 2 ohms. So if you add these two up, the equivalent resistance here is 5 ohms. One of the things you're going to be doing in your circuits is you're going to be redrawing the circuit with the R equivalent. Like, what's the total resistance? That's going to be one of the things in our tool bag to solve these problems. Go ahead.
Are those R's?
Yes, these are R's. R1, R2. R1, R2, 3 ohms, 2 ohms. 3 ohms, 2 ohms.
That's an omega.
Yeah, that's an omega.
Oh, God.
Is that better?
Yeah.
Slightly? Yeah. My little scribbles there after the number will be omegas.
Okay.
Yeah. Yeah, no, they're not pretty. Look in the book for the nice omega where they do the good, where they come in like this and they curve out and then they pinch it off and then, yes?
Yeah.
Okay, that's what it should look like. So something more, I can't draw it. All right. And this will look like redrawing the circuit. You just replace these 2 resistors with one resistor that has a value of what? 5. Okay? So this is an equivalent to this, and that'll be a useful practice. Okay? So a bunch of things are going on here. I'm showing you how to draw resistors in a circuit, showing you R equivalent, that when they're in series like this, they just add up, and then that if they do add up like that, you can redraw the circuit as if you have one resistor. Questions before we move on to, there's like 3 different things here. Questions before we move on to parallel, the other way we're going to wire these up. Can I erase over here? Everybody, we don't need this anymore. So now we're going to have 2 resistors in parallel, and I'm going to draw, this is just part of the circuit. Everybody understands this is not a complete circuit up here, right? We're good with that? This is a complete circuit. You're going to be hooked up. You got to loop around eventually. Okay, got to close the circuit off eventually. This is a complete circuit. This is just part of it. I'm just showing you from here to here. Similar idea. I'm just showing you part of the circuit right now. I'm going to call this R1 and R2. These do not add up the way that they do in series. Okay, and they're not in series. How do I know they're not in series? Well, the current comes in, okay, or the river flows in, and it branches off. And some of it goes through R1, and some of it goes through R2, okay? But certainly, okay, it's not this case where all of it that goes in one goes in the other. So right away, I know these are not in series. But now I have to see, are they actually in parallel? Okay? And this is going to be a little bit trickier, and it's probably not going to be 100% understood right now. But for them to be in parallel, the potential difference, or the voltage across the resistors, has to be the same. Now, you're going to read about voltmeters. We're eventually going to use voltmeters to measure voltages in simple circuits. We're going to get resistors out and build some stuff, okay? But for now, all you really have to do to figure it out is take 2 fingers, okay, and put them across the resistor, okay? So we can measure potential difference from my left index finger to my right, yes? Okay? So there's a potential here and a potential here. There's a potential difference. If you can move your fingers, this side of the room, can you guys still see? Yeah. Okay. If you move your fingers along only wire, only wire, only wire, only wire, only wire, and don't go across any other components, meaning batteries, capacitors, or resistors, those 3 things I drew before, okay? All I moved along was a wire, and that's it. And you can end up across the other resistor, okay? That potential difference will be the same, okay? Because we're not worried about any resistance due to the wire itself, okay? So we're going to say that if it's connected by a wire, it's the same potential. So we have the potential here is the same as here, the same as here, same as here, same as here. So these 2 potentials are the same. The potential here is the same as here, same as here, same as here, same as here. So these 2 potentials are the same. So the difference will be the same. That's how you know if something's in parallel, if the resistors have the same potential difference. How can you check after you draw your circuit? Put your fingers on there and just slide them around. If I had a resistor right here, R1 and R2 would not be in parallel because one of my fingers would go over something other than wire. How many people, at least today, think they understand not the theory of this, but just the practical, what I'm doing with my fingers, the thing I'm doing with my fingers? Because if you can do that, okay, it's going to help a lot when you do the problems, and you'll gradually get the understanding of how that all works with the other stuff. Now, you guys have had POE. You've done some simple circuits. In here, I'm going to warn you. You're going to be like, oh, I can do this because I've solved these circuits in POE. Maybe, okay, if you really knew what you're doing. Do you think our circuits are going to get far more difficult than what you had in POE? Yes. Okay. Lots of resistors, lots of loop roots, lots more algebra than what you had in there. I believe. I'm not sure, but I believe they're going to get a lot more involved. You may have had more components, but our math part is going to be tougher. Okay. So let's see. That was series and parallel for resistance. We will. I don't want to. Didn't finish this off. Hold on. So here is my actually putting this into a battery, or excuse me, into a complete circuit. So here's my R1, my R2. Here's my battery, however many volts that is, 5 volts, whatever. And to get R equivalent for this one, it's different. Okay, the book and your table or your equation sheet might write this slightly differently. Okay, what's really going on here is 1 over R equivalent equals 1 over R1 plus 1 over R2. But I found that when students use this, they end up solving for 1 over R equivalent. Okay, and you want R equivalent. So don't stick this one in your memory. Okay, the one I think you should stick in your memory is that R equivalent, okay, or the overall resistance here, the total resistance, is 1 over R1 plus 1 over R2, parentheses to the -1. Is everybody okay mathematically that those are the same thing? I just took the inverse of both sides. Yes, okay. This is what I use. This is what I recommend that you use. You get this, and then you're like, oh, I got to raise to the -1 to get my answer, so that you don't accidentally solve for 1 over the variable you care about, because you're going to get stuff all wrong if you do that. Okay? So it works differently. Why it works this way, you'll see in the reading, and also in our problems, you'll start to understand why it goes this way. Maybe even today, if you have great insight. Questions on just the algebra of this. This is the one that I recommend you get stuck in your brain to avoid common mistakes. I see it every year. People will solve for 1 over R equivalent and nothing makes sense. Now we're ready for, soon. Might be in the reading, but soon we'll do something similar to capacitors, but I don't want to confuse you today because capacitors are the other way around. And we'll talk about why for capacitors probably on Monday after you've done a couple problems with these. Next up, we have 2 rules we're going to talk about. Junction rule and loop rule. The book will call the loop rule Kirchhoff's law, I think. And I think it calls junction rule. Okay, but they might call it slightly different names. Don't get too caught up in the names. There's 2 other things that we can do to solve our problems besides combining resistors like this right now. I'm going to start with the junction rule because I think that's the easier one. Okay. Go ahead and draw a battery, and we'll have a couple of resistors in here. Oh, okay. I will never draw them that messy. I apologize. There we go. Good enough. Okay. And I'm going to put dots where there are junctions. By junctions, I mean forks in the river or places where the pipe splits. So is there a spot up here where the pipe splits right here? Yes. Okay, so I'm going to put a dot there just to remind myself that that's a junction. Okay. Is there a spot here where the river splits? Okay. Here comes the river. Okay. Imagine floating along the river, floating around the river. Oh my gosh. Okay. Inner tubes. You guys are all in inner tubes, and we're floating along. Okay. We're representing the charge. Floating along, floating along. Some of you are going to go this way. Some of you are going to go this way. When do you meet back up? Right here, before you go back to the battery. Yes? Okay. So there's a junction there. And what you can do is, okay, you can talk about, yes, I could draw this differently. Let me draw this one more way just to make it look like what we just had. This is the same picture as this, if that helps you see it better.
So is there always an even amount of junctions?
No. Oh, wait, an even amount. I never thought about that. Even amount of junctions. 1, 2, 3. Wait. 1, 2, 3, 4. Yeah, I think so. That's not important in solving problems, but yeah, I think so. Yep. Okay. So the junctions. No, because I don't think it helps you at all in solving problems. So the junctions here, I don't know why I put it there. Okay. So the junctions here are here and here. Okay. These are the same difference as each other. Okay. And at those junctions, you can say stuff about the current or what the river is going to do. Let's say that we have some current coming in. I'll call it I total. Okay. And here's R1 and here's R2. Well, some of the current's going to go through R1. Typical notation, you call that something like I1. Makes sense? The current through resistor 1 when it splits. And R2 would be something like I2. Yes, yes, yes. No big deal there. Okay. So picture the river coming in. Some of it goes this way. Some of it goes this way. How do you think they're okay with that? River splits. Not necessarily. If R1 and R2 are the same, it'll be an even amount. If R1 and R2 are different, it'll be a different amount. And that's the Ohm's law part that we're going to get into in here in just a minute. Yes?
If you have not a number of junctions that two had three split off and then two of them met back up before the other one came back.
Yes, he's right. You could have an odd number. And again, you guys, the even odd number stuff is not important at all for solving these problems. So don't get focused on the even odd number thing. That is, like, in terms of understanding, you can be a 0 and you will be perfect in electricity and magnetism. Are we good? Let's leave the odd, even stuff behind. Okay. So what equation could you write here? Okay. A useful equation would be that I total. Not rocket science here. What does I total equal? I1 plus I2. That's it. How many were all right with that? I total equals I1 plus I2. Yeah. Current that's coming in. Some current goes this way. Some current goes this way. It's got to add up to I total. Simple as that. Okay. And you can do that in any junction. There could be a split to 3, a split to 4, or whatever. But the current that comes in has to equal the current that goes out. And does that fit with our analogy for current of water flowing in? The water coming in has got to equal the water going out. Sure. You could have picked here. Okay. Before it goes back to the battery, this is I total again. This is the total current coming out here. This is total current coming out. So I1 plus I2 equals I total. Any junction you can do this at. So when you're like, I'm stuck and I don't have enough equations, one of the things you can do is the junction rule. Okay? The next thing we can do is the loop rule. Questions before I erase? The loop rule is a little bit trickier, but we're going to have an analogy to help us again. And we're going to add one more thing that you have to do when you are solving these problems. Initially, the first wave of problems that you do, probably most of them this weekend, okay, you'll be like, I don't have to do this to get the right answer. I promise, eventually you're going to have to do this to get the right answer. So it's kind of like, again, way back to regular physics. When I made you draw pictures, and I said, you got to define which way is positive, you got to draw free-body diagrams, because it's going to get tougher. It's going to get tougher, okay? So I'm going to put a plus or minus on the battery. You already know to do that. Whenever you start one of these problems, certainly before you do the loop rule, okay, but typically at the start of the problem, you have to guess the direction of current. Now, on the early problems, your guess for the direction of current will always be, I hope not, will always be correct, because they're straightforward. But eventually, you might guess the wrong direction for current because the problem is very involved, okay? Because the problem is very involved. And that's okay as long as you do what I'm about to do next. So I'm going to guess a direction for current. Current's the flow of positive charge, and I only have one battery and a pretty simple setup. I'm going to claim the positive charge will go from here this way to the negative terminal. Make sense? Yes? So I know our guess is right, but I'm still going to call it a guess. So I'm going to say current coming out of the battery goes that way. And if I have branches over here, okay, here's another branch off here for the current. We got a junction, okay? I'm going to guess the direction for the current in those as well. Well, again, I'm probably going to guess right on this one because it's not too involved. I'm going to say when the current gets here that some of it's going to go this way and some of it's going to go this way. Does that make sense? That's going to off, branch off, and then come back together. It's going down through the resistors before it meets back up. Yes? Okay. And now based on this, you have to define where the higher potential is and the lower potential is. So once you pick the direction for the current, okay, where the current comes in, positive. Where the current goes out, negative in terms of potential. So this is a potential drop going to the right. Okay? Here, I'm going to do it again. I'm going to add a plus and a minus. A plus and a minus. And wherever you enter is the plus for your guess, and wherever you leave is the minus. At the end of a problem, if you guessed wrong, you'll know because you'll get a negative current. Okay? And then you'll be like, oh, current really went, if your answer is negative, that means it's not going this way, it's not the positive and negative, that means it's going the other way. So don't sweat which way you guess, just commit to something and don't change it at all until the problem is over, completely over. And then you can be like, oh, I guessed wrong. Okay? That will come up in problems in AP Physics. More important thing, put plus minuses on your resistors. Typically, you want your resistors in a normal fashion are going to be voltage drops. Now the analogy in the loop rule. This here is our battery. Call it like 12 volts. Now we do need Ohm's law. So you read about Ohm's law. V equals IR. That can be applied to the entire circuit, okay, with an R equivalent. That can be applied to individual resistors. This can be applied whenever the heck you want. Okay, that is one of the big tools. It's like F equals MA. Okay, you can apply it all over the place, and it's going to be used in almost every circuit problem you do. You're going to use Ohm's law. Okay, so this is a real big important equation, and it works just fine over normal temperatures and for everything we do in AP physics. If you go really low temperatures, you get superconductivity, and there's times when this starts to break down, but not for our class. Okay. And our battery here is a gain of 12 volts. So the current's going to go this way. So we're going to talk about going this direction through the battery. Batteries are gains typically. So if I'm saying the current goes this way, when we go through the battery, we want the potential to go up. Is everybody okay with that? It's simpler than that though, because this is positive and this is going to be negative. The long end is the positive when you hook it up to the battery. But it is a gain. That's a gain. And the resistors will be drops. So in the analogy, the battery is going to be like the first hill, okay, and this is just an analogy. This will fall apart at some level. The analogy is going to be that it's like a roller coaster, and this is the first hill, okay? And we're in the cars, okay? We're representing like the net positive charge that's going to move through the circuit. And on that first hill, okay, something pulls you up. Yes, there's like a chain or something, old school wooden roller coaster. Are we good with that pulling up the hill? You guys visualize wooden roller coaster. You go up the first hill. Alex, you with us? Yeah. Okay. So we go up the first hill, okay, and we go up 12 volts. And now we're on our ride. Okay. And this is us staying at the same elevation for a while, okay? And now all of a sudden we have a drop, okay? And how much of a drop? Okay. A V equals IR drop. Okay. So whatever the drop is across here would be the current through this resistor times the resistance. So we go down, okay? Now we get to here, okay? And now the analogy starts to fall apart a little bit, okay? Because for a roller coaster, we're not going to branch off. We're going to just have a loop, okay? And this is the loop rule. So we've got to decide, okay? It's like we have a track and we can switch. Which way do you want to go on your roller coaster ride? Do you want to go through this resistor or this resistor? Does anybody really care? Which one? The one on the right. All right. So we're going to go through this resistor. So we're going along. And now here's our next big hill. Ooh, we're going down a hill. Okay? And at this point, we're back at the level we started at before we went up the hill. Okay? Well, what's going on here, okay, with the analogy, is that whatever you go up, you have to go down. Okay? That's the idea that gains equal drops. Gains equal drops. So whatever voltage you go up, at some point before you get back to the end of the ride, you have to go down. But it's a roller coaster, so you have to make a loop, okay? And it's the whole loop rule thing. You've got to go in a loop. The loop you take is entirely up to you. So I'm going to get a different colored marker here, maybe. Yes, I'm going to get a different colored marker here and show you the loop that we just did. Here's what we just did. That was our roller coaster ride. That was our loop. So up the first hill, and then down a hill. Down a hill. Now we're back at the level we started at. We want to ride again, we've got to go through the battery. Up the hill, down, okay? How many people, the analogy will break down eventually, but how many people are okay up till this point? We're okay up to this point? Follow along? Mathematically, what will this look like, okay? Well, this is 12 volts, okay? And let's say, I'm not going to plug numbers in for all of this, okay? But I'm going to define this voltage here. I'm going to give this an R1, call this R2 and R3, so that I can say the voltage across the 1 ohm resistor is I total times like R1. So what I can do here is say the gains, 12 volts, equal the drops. Some of you will prefer to say gains minus drops equals 0. Mathematically, is gains minus drops equals 0 the same exact thing? Yes. Okay. I'm just going to say absolute value that the gains equal the drops. Okay, that the size of the gains equal the size of the drops, because the roller coaster ride analogy holds up here. And our drop across this one, I'll write it as the voltage across resistor 1, or could I put in an IR, the current going through resistor 1 times R1? Yes, you're starting to see how this connects to those other equations, right? Because you got I's in the other equation. But for now, I'll just do V1, the voltage drop across resistor 1. Now, what's the other resistor I went across? R3. So I can write a plus V3. So here's my gains, and here's my drops. Another loop we could do is we could loop through R1 and R2, okay? And all that will happen here, I'm going to do it, is 12 volts equals, we're still going to go through V1. I'm taking this other loop. It'll be plus V2. Well, guess what? Okay, you're starting to see connections here. V1's got to be the same. It's the same variable. You good with that mathematically? Same variable. Okay. This means that V2 must equal V3. Guess how V2, guess how R2 and R3 are hooked up? They're hooked up in parallel. Look, my fingers across R2, same potential difference here. All I'm moving is across wire. There's no components, so they're hooked up in parallel. They have the same potential difference. It's backed up here by the loop rule. Backed up here by the loop rule. Lots and lots of stuff to wrap your head around. This is to help with the reading. We are not done. It doesn't mean much until we start solving problems, so let's go ahead and solve a problem. At this point, if you haven't written anything down, you need to. So get out your composition notebook. I'm going to give you a problem. We're going to solve it. We're going to try to put all of this together, but I'm going to walk you through it. You can just keep watching or write. It's up to you.
Okay.
Yeah. How much time are we up to there in that thing?
25, 45.
25? Okay, that thing doesn't usually die, I think, for about 30 or 40 minutes, sometimes longer. If it's straight video. Well, it's not meant to. It's meant to 10-second videos, not 40-minute videos. All right. So let's make up a circuit. And you guys got calculators, so I don't care about the numbers, but I'm going to keep it kind of low. Let's call this 10 volts, although I've never seen a 10-volt battery. I'm sure they exist, but 9 volts, 12 volts, 1.5 volts. All right. And let's go ahead and we'll keep this pretty straightforward here initially. We'll just have 2 resistors. This will be a 3 ohm, and this will be a 2 ohm. And let's assume that we want to find, and there's lots of things I could ask you to find. Okay? It's kind of like projectile problems again. I could ask you to find the voltage across the 3 ohm, the voltage across the 2 ohm. I could ask you for a current total. I could ask you for R equivalent. I'm only going to ask you for one of those things, and we'll end up doing a lot of them. Okay? I'm going to say, what is the current, and the TOT stands for total, in this problem. So what is the total current coming out of this battery? What's the total current coming out of this battery? Step 1, okay? Find R equivalent. So the first thing we're going to do is we're going to find the equivalent resistance, and it's got some special name in the book, Thevenin equivalent circuit or something like that, something with a THEV. Do you know what it is? What? Thevenin, yeah, something like that is what we're about to do. It's another name for it. And we're going to redraw our picture, and we're going to combine our resistors into one resistor. And that's a step-by-step process, but we only have 2 resistors, so it's not a very big step here. Okay? All the current that comes out of the battery, almost forgot. We got to pick. Okay? This is plus and minus by how you define it. Current, I'm going to guess, is going this way, so this will be a plus and then a minus because we want the resistors to be drops for our guess of the direction of current. And this will be a plus and a minus because we go around the corner. Is everybody okay with my plus minuses on my resistors? Yes, yes, yes. Okay. So let's get R equivalent. So these 2 resistors, are they in series or parallel? Series, because all the current that flows into 3 flows into the 2. So I'm going to look at this part of the circuit right here, and I'm going to replace it. I'm going to replace it with one resistor. And I'm going to say that that new resistor is just, I'm going to call it R3 plus R2. Again, I'm showing you the process. I know the numbers up here are easy. Okay, and that'll just be 3 ohms plus 2 ohms. Again, those are my ohms. That's a unit. Okay, we get 5 ohms. And then I redraw the circuit. Okay, so I'm going to redraw the circuit with one 5 ohm resistor. Is there anything else that I need to, are there any other resistors that I need to put together here? No. But that's the process. You just do 2 resistors at a time, okay, or however many are in series there at a time, and then you redraw, and then you deal with the other stuff. That's why I have this dotted line here. Okay? So this actually is my R equivalent, the 5 ohms. I'll give you guys a second to catch up. And hopefully, I'm trying to keep it to this middle board. You know, organize your work a little bit better than this up here. When I'm using both boards, I'll spread stuff out. Because I'm going to have to erase here in just a second. Now, we don't need to use the loop rule or the junction rule, because I just asked for I total, and we just have one resistance and one voltage. So we're just going to apply, we can apply Ohm's law anytime we want to any resistor, okay? I'm just going to apply Ohm's law right here, okay, and say that V equals I total times R equivalent. This, if this is the voltage of the battery, and you only have one battery, okay, to get current total, this is what you do every time. To get the current coming out of the battery, or the total current you're working with, you just have the voltage of the battery, if there's one, okay, your equivalent resistance, and you can get your total current. That's not going to change. Yep.
This would be like a lowercase I and a capital I.
Where did I do that?
Or just previously you put a capital I.
Oh, The way Ohm's law is traditionally written is just like that. When we actually start defining currents, I like to use the lowercase i's. It doesn't matter. You can use capital I or lowercase I to your pleasing. Yep. Some books will use capital I for current total. Some will use a lowercase. I will usually put subscript so you'll know which current I'm talking about. I'll have an I total, an I1, an I2, that kind of thing. All right. It does not matter. Your personal preference. Just put a subscript on so everybody knows what you're talking about. So we can get this now. It's plug and chug. 10 volts equals I total times R equivalent, which was 5 ohms. So I total, 10 divided by 2, is 2 amps. I know you're not familiar yet with the units, but I total is 2 amps. That's all well and good. So we answered that. Now what if I ask for the voltage drop across the 2 ohm resistor? How do you think you would get that? Nobody? Yeah, okay. You have the current going through 2. Why? Because all the current that comes out of the battery is going into 3 and going into 2. Yes, because they're in series. So you know the current, okay, through the 2 ohm resistor. It's I total. So I2, the current through 2 is I total. Questions on that before I plug in the numbers? All right. So let's go ahead and get what that is. So I total is, I already forgot, 2 amps. And the resistance of 2 is 2 ohms. So we get a voltage of, or a voltage drop of 4 volts across that resistor. Give you a chance to catch up here. And there, by the way, if you're like, oh, we could have done it a different way. Yes, there's like, not 8, but there's 2 or 3 ways to attack every single problem. And I'm going to switch it up on the resistance for 3. I'm going to use something else intentionally. Yeah.
So at every spot along the circuit, the current is always going to be 2 amps.
Because everything's in series. The battery and the resistors are all in series with each other. So they all have the same current. If we have branches, that will change that. Yeah. I started with the simplest example, short of 1 resistor that I could think of. Because even 2 in parallel hooked up to a battery is slightly more complicated than this. All right, now, could we do the same thing to get the voltage at the 3? Could we take 3 times 2 and get 6? Yes. Or we could do the loop rule, okay, just in our heads. Okay? Here we go, 10. No, not in our heads. This is the first time we're doing this. Gains equal drops. And again, organize your paper slightly better. I'm trying to keep it on this middle board and not erase everything. Gains equal drops. We go up 10, and then the voltage across the 3 is what I'm looking for, and then we go down across the 2, what? 4 volts. So what does V3 have to be? 10 minus 4, which is 6, okay?
GG.
Which is the same thing as our 2 amps times our 3 ohms. It's all consistent. It's all consistent. If you ever get a contradiction, then you've done something wrong. You've misapplied a rule or you've messed up your algebra. Probably messed up your algebra. Yes?
Is your V3 that is supposed to represent your voltage at the first resistor?
Yes, voltage across the 3 ohm resistor.
Oh, okay.
Yeah. So I'm calling this R3 and R2 because I just have simple numbers. If this was like 2.5, I wouldn't do that. I'd label them R1, R2, or something like that. Okay. So we get a 6 volts. I was going to have you try one. Okay. Obviously, we don't have time for that right now. Just let me show you briefly. Stay tuned in. This is going to help you guys over the weekend because you're going to be doing some of these problems. But they're going to get shorter. They're going to get more selective.
It is Friday, March 7th, a white day. Congratulations to
2 resistors in parallel. If I throw one in here like this, okay, to get our equivalent, take care of the parallel ones, redraw. And then you'll have something like, I'm going to have you do some of these. Whoops. That's pretty good. You'll end up with, after you combine these two, how? 1 over this R plus 1 over this R to the negative first. And then you literally take that out of your circuit and put that value in its place. And now you have 2 resistors that are in series. Because the one that this replaced, right here, will be in series with the other one to get R equivalent. So when you start mixing series and parallel, be careful on your R equivalents when you combine the stuff. Obviously, there's example problems and stuff in the reading as well that will help. Okay? This assignment will get smaller. I'm going to take some of these problems out because we didn't quite get the complicated example that I wanted to today. All right, you can stop. Thank you. Hey.